Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abutewa Sos Ugobela Mets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 8, still on electric circuits, episode number 9. So it says the battery in the circuit diagram below has an EMF of 6 volts and an internal resistance of 0.4 ohms. So note that we are given the internal resistance. It's 0.4 ohms. Right. Then 8.1 says with both S1 and S2 open, give the reading on V2. So we have seen a question like this before. We already know if they put our voltmeter here on an open switch, this voltmeter will be directly linked to the battery, right? So that means it will be reading the voltage of the battery, which is the EMF of the battery, right? So it's directly linked to that. Remember, there is no current flowing in these resistors, so these resistors are basically ineffective at the moment, right? So the reading on V2, if it reads the EMF of the battery, then it has to be 6 volts. So easy peasy like that. We now understand how to approach that question. Then 8.2 says, with only S1 closed, the ammeter records a reading of 0.75 amperes. Explain the meaning of 0.75 amperes. I know that this can be a weird question, but then these questions can be found in your grade 10. So they kind of haunted you with your grade 10 here. Let's see how we are supposed to explain that. So we say, there is a flow of charge of 0.75 coulombs per second, right? So that's the meaning of that. Now, where do I get that? I get it from the fact that we know that current is I is equals to Q over delta T, is the rate of flow of charge, right? So the 0.75 amperes is the same as 0.75 coulombs per second, right? Remember, charge is given in coulombs and then delta time is given in seconds. So the 0.75 amperes, the meaning of that is that we have 0.75 coulombs of charge per second, right? Okay, so now let's proceed to 8.3. So to answer 8.3, it says write only with only S1 closed, meant to say, with only S1 closed, calculate the external resistance of the circuit, 3 marks. Now, a 3-mark question means that you have to use the information that you are provided with here. It's a straightforward question, formula, substitution, and the correct answer. Now, from here, we can see that we cannot calculate the external resistance of the circuit simply by calculating the resistors in parallel and also add it to resistor in series, because we don't have resistor R here, which we can see that we are being asked to calculate that in 8.3.2. So now we must think of other ways to calculate the external resistance. Now, if we go back here, we are given the EMF, and then we are given the internal resistance. Now, the formula that comes to mind is obviously E is equals to I, and then bracket R, and then small r, right? So it's always a straightforward thing. Then the 0.7 amperes, remember, when they close switch S1, then your ammeter here reads 0.75 amperes, which we know it reads the total current. So we have the total current, we have the EMF, we have the internal resistance. The big R that we are looking for is the external resistance. So that's how we now gonna calculate that. Then current is 0.75 R, that's what we are looking for. Small letter r, internal resistance is 0.4. Now we know the drill. In order to be more efficient with your maths, start by dividing by that 0.75, and 6 divided by 0.75, that's 8, and then R plus 0.4. So that means our R external is just a matter of saying 8 minus 0.4, which will give us 7.6 ohms, right? And just like that, now you have calculated the R external. Okay, awesome. Now let's proceed to 8.3.2. Now it says calculate the resistance of resistor R. We already know that R external is R parallel plus R series. But then if we are closing only S1, then where are the resistors in parallel? So we know that the current flow go like that. So no current will pass here because S2 is open. So no current will flow there. So the minute it gets there, there's a splitting of current. Some of the current goes through resistor R, and then some of the current will split and go through the 3 ohm resistor and the 1 ohm resistor, right? So where we have different colors, we already understand it indicates that the resistors there are connected in parallel. So there again, we have our full total current passing, right? Okay, now let's understand this, right? Note that we are faced with the same situation from the previous question, whereby we need to take these two resistors that are in series and then combine them to form one big resistor that will be in parallel to R, right? So now at this point, we understand that this is in series, and then here we have our parallel branch, right? So it is very, very important that you analyze the question before you can even start answering. A lot of you are so concerned about having to answer questions, but then you forget that analyzing is the key to answering the questions correctly, right? Now our R external, we did calculate it 7.6. Then our R parallel, fortunately we can't calculate it. So we do have the R series though, it's 4. So to find our R parallel, it's simply 7.6 minus 4, right? Which will give us 3.6 ohms. Now at this point, we can find R by simply saying R parallel is equals to R1 multiplied by R2 over R1 plus R2, product over sum formula. Now remember, we have already combined these ones. So all we are seeing here is a 4 ohm resistor. Then RP is 3.6. R1, let's just say it's a R. Then R2, let's say it's the 4, the combination of these two resistors. Then R1 again, it's, pardon me there, I must say multiply instead of plus, yes, and then plus 4 again. Now all we have to do here is cross multiply here. So 3.6 bracket R plus 4 is equals to R times 4 is 4R. Now obviously at this point, what do? We can multiply inside here 3.6R, and then 3.6 multiplied by 4, we get a 14.4, and then it's equals to 4R. This point we can just take the 3.6R, transpose it over to that side. So that's 14.4, 4R minus 3.6R. Now we have 14.4 is equals to 0.4R, which we need to then divide both sides by 0.4, right? Now what is 14.4 divided by 0.4? Then when we do that, we are supposed to find our R is equals to 36 ohms. And just like that, we have calculated the value for R. So R has to be 36 ohms. So pay attention to how I went about solving that question. So yes, you might argue that for a 3-mark question, this was a bit long, but then yeah, if you have a better way of doing it, you can try that one. Let's proceed. So this question still continues on the next page. Okay. We have 8.4. It says S1 is now open and S2 is closed. How will the power dissipated by the 4 ohm resistor change? Right? Only increase, decrease, or remain the same? Explain the answer. So they're saying S1 is now open and S2 is closed. Let's go back to our circuit. So S1 is open and S2 is closed, meaning that current, what happens to the current now? Current now flows in this direction like that. So it can't flow to this part. So all of these resistors are now effectively cut off. Now we only have that resistor in series, right? Now, if you go back to the previous question, we had calculated that our R external was equals to 7.6 ohms. But now with only S2 being closed and then S1 open, that means the new R external is now equals to 4 ohms because the only resistor that is there is this one that is connected in series. So now what is the observation? The observation is that the R external decreases, right? Now we know that if R decreases, then according to this relationship here, R is inversely proportional to current, then we expect our current to increase, right? But then we've been asked about the power, right? So what will happen to the power? Now we know that according to P is equals to I squared multiplied by R, P is directly proportional to current. So if we are saying current increases, then we are also expecting power to increase. So that's basically the explanation. But then let's check how we would actually put it. Let's check how we would actually put that. So we'll say it increases. Now, number one, the total external resistance decreases, as we have proven. The total current obviously has to increase. Then P is directly proportional to current, so power dissipated increases. And that's how you were supposed to put that, right? So for 4 marks. So a mark for having to say increases, and then 3 marks for all these points. So we can see 3 points: observation, relationship, and the conclusion. Okay, so now let's proceed to 8.5. So it starts by this statement here. Grade 12 learners conducted an investigation to determine the internal resistance of a battery. The circuit used is shown below by varying the rheostat settings. So the rheostat settings, or the rheostat, is basically the variable resist. So that means you can change the resistance of that particular component. Then the corresponding values of the circuit current and the potential difference V2 were recorded. Okay, the results obtained were used to plot the graph below. Now 8.5 says from this graph deduce the EMF of the battery, and it's only a mark, so it shouldn't be that hard. Now it comes from understanding that EMF is simply the total potential difference when no current is flowing. So if you say when no current is flowing, this simply means when current is equal to 0. What is the potential difference when current is equal to 0? It should be this one here. But then first we need to get the interval of this graph here. So looking at this, we have 0 and then 2 blocks here, then 1. So from here, if we want to find the interval, we can simply say 1 divided by how many blocks were jumped in order to get to 1. It's 2. So that's 1 over 2. It gives us 0.5. So which means our interval here is 0.5. So that's 0, 0.5, 1, 1.5, 2, 2.5, like that. So which means the value at this point has to be 4.5. So the EMF, in other words, for 8.6.1, the EMF has to be 4.5 volts, right? So it's easy as that. Now, 8.5.1 meant to say. Then 8.5.2 says calculate the internal resistance of the battery. You will remember that I once said this, that if you are given a potential difference versus current graph, then you must know that the gradient is the one that will be representing the resistance. So in this case, if we want to calculate our internal resistance R, then we must know that we can find that by just using the gradient formula, right? Because the resistance is represented by the gradient of the graph. So, but then the one thing that you have to note, normally our graph looks like this. It's an increasing graph. Now that we have a decreasing graph, we must note that in this case here, the gradient will represent the internal resistance. But then in the case where we are given, the gradient actually represents the negative of the internal resistance. Because remember, a decreasing graph has a negative gradient. Right. So this is a way to indicate that we have a negative gradient. Okay, so now this is how we will calculate this. So to calculate, we'll say to find our gradient here, it's simply just change in y over change in x, which in this case, it is change in the voltage over change in the current. Now, obviously from here, we can see that this resembles R is equals to V over I, which is why we are saying that the gradient represents the resistance. So note that. So, okay, can simply choose to take this point and the 0 here, and then take the total current and the 0 there. So basically, I'll just go 4.5 minus 0. And then down below here, I have to take the x value that corresponds to the 4.5. So it's 0. And then the x value that corresponds to this 0 here is 7.5 from here. So I hope that makes sense. So I'm simply using this. So let me indicate so that no one is lost. So basically this is my y2 and then this is my y1, right? And then now I have, this is my x2 and then this is my x1. So we know that it's y2 minus y1, x2 minus x1. Okay, so now to calculate here, simply punch all of that into your calculator. You get negative 0.6. But then remember we said the gradient is equals to negative R. So if our gradient is negative 0.6, what is our R? We need to then divide by -1 both sides. Then therefore, our internal resistance is 0.6 ohms. So make sure that you pay attention to that and understand what the gradient of the graph represents. The gradient of the graph represents the resistance, right? So to find the internal resistance, I simply used the maximum potential difference, which is the EMF, and then also the total current. So we know that supposed to give us the R internal, right? So that's how you were supposed to tackle this question, all for a total of 17 marks. So it was a pretty nice question. So if you have enjoyed the lesson and then you found it helpful, please press the thumbs up button. And then if you've been watching the videos and haven't subscribed yet, please hit the subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.